Welcome back to today's Explainer, where we're diving straight into a totally awe-inspiring intersection. We're talking about the exact point where abstract fractal mathematics crashes right into computer science architecture. We're going to look at how theoretical concepts that usually live purely on a university chalkboard, stuff like infinite recursion and perfect geometric scale, are literally being used right now to completely re-engineer how databases handle growth. So if you've ever wondered how on earth abstract math becomes, highly functional code, you are absolutely in the right place. Okay, let's dive into this. The core problem we're facing today is kind of a fundamental clash of realities. See, computers, no matter how ridiculously powerful they get, have finite memory, right? They rely on physical RAM, hard drives, bounded processing power. But mathematical structures, a lot of them grow infinitely. They branch out forever, never stopping, never hitting a physical wall. So the ultimate question for database architects is this: how do you take an infinitely growing mathematical organism and map it onto a finite, physical machine without causing the whole system to immediately crash and burn? To figure that out, here's our roadmap for today. First, we'll hit the infinite recursion problem. Then we'll enter the world of Pythagorean metal and map out the coordinates of scale symmetry. After that, we'll look at the point at infinity loop, figure out building the fractal database, and wrap up with surviving the Stack Overflow. Starting off with Section 1, the infinite recursion problem. To really appreciate the genius of the solution we're about to explore, we first need to understand why standard relational databases absolutely despise infinite data structures. Non-halting recursion is basically a software engineer's worst nightmare. It's the kind of thing that wakes you up in a cold sweat. By definition, it's a programmatic or mathematical process that just invokes itself continuously, right? There's no terminating base case. So imagine telling a standard database to query a nested data directory, but that directory structure literally has no end. The engine will just keep digging deeper and deeper, allocating more and more temporary memory for every new nested level it finds until, bam, it exhausts all available resources and crashes your entire system. That's your classic Stack Overflow. But what if we flip the script entirely? What if we didn't treat non-halting recursion as this fatal bug? What if, for a very specific type of hierarchical database, this endless recursive looping was actually the actual engine of its dynamic growth? That brings us to Section 2. Enter Pythagorean metal. Now, what's really interesting about this slide is where the math gets incredibly fascinating. We're looking at a mathematical framework called Pythagorean metal. This was developed by Kyle McLean Smith specifically for the seed tree DB architecture. If you look at the classic right triangle here, where orthogonal sides A and B yield a diagonal C, there's a neat trick. By algebraically removing the orthogonal measures from that diagonal C, you're left with a very specific ratio, x equals C minus B all over A. Now, within this framework, this irrational non-halting value isn't just a random number. Actually, it becomes a scale symmetry base. It essentially creates a mathematical loop that perfectly scales towards infinity without ever losing its fundamental proportions. So we're basically reimagining classic Euclidean geometry into a functional foundation for computation. How cool is that? And this brilliantly illustrates exactly what we're talking about. Look at these nested squares. They represent a strictly self-similar fractal, which is specifically related to the Pythagoras tree. In the context of our database, this translates into what's known as a resonating rectangle. Because of that scale symmetry base we just discussed, this rectangle acts as a non-halting, self-reproducing automaton. Meaning, every single time you zoom in on a subbranch, you find a perfectly scaled-down copy of the entire parent structure. The math itself dictates that it can generate an infinite stack of unique input-output data points. They're perfectly ordered, and it does this without ever breaking its own structural rules or needing some external process to step in and manage it. All right, moving right along to Section 3, coordinates of scale symmetry. So we have this beautiful, elegant fractal math, right? But to actually map real data, you need coordinates. And instead of using your standard arbitrary X and Y grid, this system uses the fractal patterns themselves as the unique addresses for the data. Research has established that geometric series, along with approximations of the silver and golden ratios, are uniquely suited to form non-halting, self-reproducing database coordinates. By using formulas tied to things like the Fibonacci sequence, the database actually gives itself a way to uniquely index an infinite stack of nested data. And because the geometric sequence never repeats and literally never halts, you suddenly have an infinite supply of unique coordinates. Plus, the structural stability is just baked right into the mathematical laws of scale symmetry. It's a real game changer. Let's look at Section 4, the point at infinity loop. This concept right here represents a massive architectural leap. If you want to treat a database as a living, growing organism, you basically have to abandon traditional cyclic loops entirely. Think about a standard torus loop around. It's cyclic, it's finite, it just spins in a set, closed track over and over again like a race car. But the Pythagorean metal architecture, it employs what's called a point-at-infinity loop-around. This mechanism pairs a finite modulo sequence, which handles the rotation and iteration side of things, with a positive and negative infinite number line sequence, which handles the fractal and recursive structures. So it allows the system to iterate through current actions, while at the exact same time diving deeper into an endless recursive tree. It's kind of like iterating through the numbers on a clock face, but with every single tick, you are also stepping deeper into a microscopic, infinitely nested data structure. Down to Section 5, Building the Fractal Database. Okay, it's time to bring all these abstract geometric concepts out of the clouds and down into the concrete realm of computer science and state management. So the crucial point is how this mathematical scaffolding dictates the actual, literal code architecture. In standard software design, developers build very distinct layers, right? You have the database schema, which acts as the nouns, and the application logic, which acts as the verbs. They're separate. And trying to get them to communicate with each other causes a ton of friction, something we call the object relational impedance mismatch. Well, the Hierarchical Script-Database, or HSDB, eliminates this entirely. By utilizing a single language environment, like, say, a JavaScript kernel, and placing execution nodes directly inside the data tree, it makes the program and the data structurally isomorphic. That's a fancy way of saying they literally take the exact same shape. Just take a look at the Mandelbrot and Julia sets here. These fractals are defined by incredibly simple recursive formulas that end up generating infinitely complex boundaries. Well, because the HSDB uses that exact fractal coordinate math we've been talking about, the application's execution path and the database's data retrieval path become exactly the same thing. The code is literally just another node in the fractal. Just as these fractals grow dynamically along their edges, the database itself acts as an application that evolves dynamically over time. The script instructions are nested right alongside the data in the self-same mathematical hierarchy, just naturally responding to events and growing the tree. Finally, Section 6, Surviving the Stack Overflow. Let's move to and see how this builds in reality, because here's the ultimate reality check. We have this theoretically infinite mathematical structure, but how does a physical, finite piece of hardware actually survive this? Traditional recursive SQL databases suffer from what we call an amnesia bottleneck. They basically forget previous states and have to hold massive amounts of data in working tables, which leads to these extremely high memory footprints that just crash the system. But by evaluating the data tree as an infinite stream, newer systems can use an algorithm called iterative deepening. This cleverly combines the completeness of a breadth-first search with the low memory requirements of a depth-first search. The result? It drops memory residency drastically. We're talking in testing, dropping from 56 megabytes down to just 2 megabytes. Furthermore, by using key-based state tracking to update states in place, the database completely bounds its memory footprint. It perfectly tracks its place within the infinite fractal without trying to somehow stuff the whole universe into its RAM. So we've really traversed a lot today. We went from the theoretical, system-crashing dangers of infinite recursion through the geometric elegance of Pythagorean metal and scale symmetry all the way down to practical, real-world stream processing strategies for bounding memory in fractal databases. By synthesizing geometry and code, we aren't just filing away static data. We are orchestrating living, self-reproducing automata that can scale infinitely on finite machines. Grasping this synthesis truly unlocks entirely new ways of building scalable systems. So I'm going to leave you with this one final thought to ponder. If your data and your code are structurally identical to a fractal, growing seamlessly through non-halting mathematical loops, what can't it build? Thank you so much for exploring this with me today.